Alaikum all. We now move to a new topic. It is optimal control theory, the Hamiltonian function. Okay, now the optimal control theory in this chapter is basically about optimization that includes time horizon. Okay, so this is the difference between this type of optimization with the previous study of optimization. Why do we need to include time horizon? Uh, if we have a business, for instance, we know that the business is not done only at a particular point of time, let's say a minute or a second or an hour only. It has to be within certain period of time, because we want to make more and more profit, maximum profit from time to time, so that we can earn more income. All right. So optimal control theory can be used to understand this. And when we talk about the optimal control theory, it is the optimization that includes time horizon, like I said earlier, and there is fixed endpoint. So it's not forever. There will be an endpoint. Okay. So one of it is the Hamiltonian. So Hamiltonian is just one example of optimal control theory. There are a lot of optimal control theories that you may learn later at the higher level, especially at the master and also PhD. Okay, so what is Hamiltonian function and why it is there? It's basically dynamic optimization of a function and subject to constraint on the state variable. In optimal control involve um, this function. Okay, so it is actually similar to the optimization where we have Lagrangian function in concave programming. You have done this in business maths, but this time it involves time. So in general, how does Hamiltonian function look like? Okay, so Hamiltonian function look like in expression 1. So if you look at expression 1 here, okay, you can see in expression 1, Hamiltonian function is a function of x and function of y and function of t. T here refers to time. Now, if you can see here, x is also a function of time. So means x can change over time. So if x can change over time, that means there is a growth in x in it. Okay, so same goes to y. Y is also a function of time. So if y changes over time, okay, then it means there is a growth for y. Okay, and then time here is exogenous variable, because you can see time doesn't depend on any other things in the system or in the equation. Now, for Hamiltonian function, if you see on the right hand side after the equation equal signs, then you can see the first term here, first function, and the second function. So the first function is usually the objective function. Yeah, let's say profit function or cost function or whatever function that we want to optimize. And the second function is usually the constraint. Okay, and then we attach lambda here. Okay, so as you can see, we have x, we have y, we have t, we have lambda. All right, now there are some terms that you need to understand in Hamiltonian. The first one is state variable, called state variable, and the last one is Lagrangian multiplier. Now, so when we look at the state variable, what does it mean by state variable here? Okay, so state variable in this case is actually xt. Okay, what about co-state variable? Co-state variable is basically the lambda. Okay, now if you see the lambda, this is the lambda. Okay, now so lambda is basically, if I write it here, this is lambda, yeah, and then this is x, depends on t. Now the lambda here also depends on time. Okay, the lambda here also depends on time. Now lambda, which is called the co-state variable, it is similar to the Lagrangian multiplier. So the co-state variable lambda t, basically what? It is actually the one that can be used to estimate the marginal value or shadow price of the associated state variable xt. Okay, so that is the co-state variable. Now, so co-state variable lambda Lagrangian multiplier. Okay, now, but what does it mean by, these two terms, state variable and co-state variable, formally. So when we talk about state variable, in this case xt, yeah, it is actually a set of variables that are used to describe the mathematical state of a dynamical system. Okay, now xt. So what about co-state variable? The second one. It is related to co-state equation, something to do with state equation used in optimal control. It is also referred to multiplier. In this case, obviously, it is similar to Lagrangian multiplier. Okay, now, next, okay, when we want to use expression 1, which is Hamiltonian function, we assume that Hamiltonian function is differentiable in y and strictly concave. What does it mean by differentiable in y? So it means that when you differentiate Hamiltonian function with respect to y, you can find the answer. Therefore, it is continuous with regard to y, and it is strictly concave. Okay, when it is strictly concave and differentiable in y, that means we can have interior solution or not, and not boundary solution. So it means when you solve this problem, when you want to find x, when you want to find y, when you want to find y, that means you can have answer for x, y, positive value in it. Okay, now there are certain conditions that we need to follow here when we want to do optimization using Hamiltonian. So what are the necessary conditions for maximization? Let's say we want to do maximization using Hamiltonian function. Yeah. So we have three different conditions here. So these are the necessary conditions. Number 1, number 2, number 3. Okay. The first one. Now, the first one is you must differentiate Hamiltonian function with respect to y. Okay, so you differentiate Hamiltonian function with respect to y, and then equate it to 0 just to make sure that it is optimization, isn't it? When you equate it to 0, the slope of Hamiltonian function with respect to y is flat. Now, usually it is optimization. Now, condition number 2, we have, equations of motion. We have the first equation of motion in A, the second equation of motion in B. So what are these two basically? So you have delta lambda over delta t equivalent to lambda dot, okay, equals to minus delta h over delta y. Okay. Now delta lambda over delta t means what? The change in lambda when there's a change in time. Or in other words, it can also be written as lambda dot. Okay, when it is written by lambda dot, it means the change of lambda over time or the growth rate of lambda. Okay, so this is the way we write, change in certain variable over time. Yeah, if you read a higher level of economic textbook, let's say economic growth, you will see a lot of this in those kind of textbook. But there's another way to find this, an easier way. The easier way is minus delta h over delta y. Okay, now the next one is the second equations of motions is delta h over delta x, which is x dot. Okay, now as you can see, delta h over delta x is written as x dot, but you don't see change in time here, isn't it? But you must remember x here depends on time, isn't it? So another way to do it is minus delta h over delta lambda. Okay, so you have the growth rate in x. Okay, now the first two conditions, condition number 1 and condition number 2, are known as the maximum principle. Okay, now and if you look at the condition number 2 here, all right, these two equations of motions are generally referred to as Hamiltonian system or the canonical system. Okay, now let's look at the third necessary condition for Hamiltonian function. So the third necessary condition here, you have x at initial point 0 equal to x naught. X at the ending point, which is t, is called xt. So what is this basically? Okay, so the third necessary condition is basically the boundary condition. So you have the lower bound and the upper bound. Okay. Now, so after that, once you follow these necessary conditions, then you need to solve the problem. And you need to apply maximum principle here, condition number 1, condition number 2, in order to get, in order to solve state variable xt and also the co-state variable lambda t. And then after that, you need to check certain conditions, and then you find the answer for both of these, and this is optimization. Now, to make it clearer, let's look at the example. So we have example here. We need to solve the optimal control problem for the following expression. Let's say maximize 4x minus 5y squared. This one should be 5y squared, not 5y times 2, and then dt. So you integrate, maximize from 0 to 3. Okay, subject to x dot equivalent to 8y, and a boundary condition here is initial point 0, x must be 2, ending point is 3, x must be 117.2. Okay, so the time from 0 to 3. Okay, now how to do this? So first, we need to set up the Hamiltonian function. How to set up the Hamiltonian function? We need to use the objective function here, and also the growth function here to set up the Lagrangian function, or the Hamiltonian function, not the Lagrangian function, yeah, because this is optimization over time. Okay, now let's do this. So first, set up the Hamiltonian function, call that function as h. So we write the objective function again here. So the objective function is 4x minus 5y squared. Okay, and then plus the constraint attached to lambda here, lambda 8 and y. Okay, all right. So we have set up the Hamiltonian function. Now, let's assume interior solution applies. Then we need to apply the maximum principle. Now, let's go back to the necessary condition, the theory. You must find number 1, delta h over delta y, and equate it to 0. So how to find it? So the first condition, okay, A, delta h over delta y. So you equate it to 0. Now, before you equate it to 0, you need to differentiate it. So differentiate it as usual. So here, minus 10y, by now you should know how to get minus 10y, plus lambda 8, isn't it? Let me rewrite it properly. Okay, so we have 8 lambda, and then equate it to 0. Now, once you equate it to 0, you try to solve it. You may get y equivalent to 0.8 lambda. Okay, now you need to show how to get y equivalent to 0.8 lambda here, because here I just jumped the steps, but you need to show how to get it, and because the steps here will be given some marks. Okay, now number 2, the necessary condition number 2, you look here, you need to find delta lambda over delta t, which is equivalent to the growth rate of lambda dot. But alternatively, you can find it this way, equals to minus delta h over delta y. Also the second one, delta h over delta x equals to x dot equivalence to, alternatively, you can use this, minus delta h over delta lambda. Okay, so now for number 2, okay, we need to find this delta lambda over delta t equivalent to lambda dot equivalent to minus delta h over delta x. Okay, so we have this one, number 1. And then, okay, so when we try to find it, then you can see the answer is minus 4. delta H over delta X is 4 because we have negative. So you put negative, it becomes minus 4. Okay, so the second one here for necessary condition number 2 is what? You need to find the growth rate of co-state variable or X dot. So this is the way you do it, delta H over delta lambda. Okay, so delta H over delta lambda is actually what? It's very straight to the point. It is 8y. Okay, but from these two, all right, what you can see is that from these two, okay, let me write the number of equations so it's much easier for you to refer to. So this is equation number 1, okay, and then this is equation number 2, okay, and then we have B here, number 3, okay, all right, but here from number 2 where we have y equal to 0.8 lambda, okay, we can have x dot like this, isn't it? Okay, we can have x dot like this. So you have x dot equivalent to 8y from equation number 3, okay, but you know that, okay, y is actually this y is actually equivalent to number 2 here, isn't it? So you can substitute it back here. So you get x dot equivalent to what? 8 times 0.8 lambda equivalent to 6.4 lambda. Okay, I hope by this, up to this point, you can understand what I'm saying. So the process is quite long actually. Now, we are employing the maximum principle. After employing the maximum principle, then we are left with two differential equations. Okay, so once we are left with two differential equations, then we can solve for the state variable. We need to find xt. What's the value of xt? We also can solve for the co-state variable, which is lambda t. We need to find what is lambda t. Okay, now, so you look here. By integrating, we need to do some integration here because we want to find co-state variable. So we need to integrate lambda dot basically. Okay, we need to integrate lambda dot. So we need to integrate lambda dot. So we have here, we have lambda dot equivalent to what? Equivalent to minus 4. Now integrating, okay, this, let's say equation, let me number it first. So this one, let's say number 4. Okay, this one, let's say number 5. Integrating 5 with respect to t, yeah? Okay, so when integrate it with respect to t, because from lambda dot, we want to get lambda, so we integrate. Okay, so integrate it, so lambda t is actually what? Integrate lambda dot dt. So when we integrate, we get minus 4 dt equivalent to minus 4t plus constant. Okay, plus constant. Let's call this constant 1. So let's call this equation 6. Okay, now what we need to do next is, once we find 6, okay, we can substitute it back into x dot equivalent to 8y. Okay, so recall back, x dot equivalent to 8y is this, isn't it, in equation 4. So we need to substitute lambda t back into that. Okay, so when we substitute it, into x dot equation. Okay, so when we substitute it, then we get something like this. X dot equivalent to 6.4, okay, times minus 40 plus C1, okay. So you get something like this, minus 25, okay, 0.6 T plus 6.4 C1, call this 7. Now, you might be questioning me, how do you get 6.4 here? Okay, so see this one, equation 4, yeah? Okay, so that's why you can see 6.4. Okay, so now we are at expression 7. So we have minus 24.6 T plus 6.4 C1. Remember, yeah, our objective now is to find the value or to solve the value for state variable xt and also co-state variable lambda t. Now, next, what do we need to do is, we have 7, integrate 7. 7 is x dot. We integrate 7, okay, so that we get x instead of x dot. So lambda dot, we integrate, we get lambda, isn't it? X dot, we integrate, we get x. Okay, but as a function of t. So now, we integrate it. Let me erase this first. Okay, we integrate x dot, so it becomes like this. So xt is actually the integration of x dot, and x dot we already found it earlier, minus 25.60, okay, plus 6.4 C1, okay, and then integrate it with respect to time, yeah. Then when you solve it, xt becomes what? Minus 12.8 t square plus 6.4 C1t plus another constant C2. Okay, so now this one is actually equation, sorry, this is not equation 7, this is actually equation 8. Okay, this is actually equation 8. Okay, now, so now remember the boundary condition. This is the boundary condition, isn't it? The necessary condition. And in this question, the boundaries are, the lower boundary is x when time is 0 is equivalent to 2. X when time is 3 is equivalent to 117.2. Now, these boundary conditions, we can now use it to solve for the constants of integration. You see the constant here, C1, C2. Okay, so you apply, you apply x0 equal to 2, x3 equal to 117.2, okay, in order to get C2 and C1. So you see here, this is C1, okay, this is C2. All right, now how to get it? So here, x0 is equivalent to minus 12.8, okay, time is 0, isn't it, square, plus 6.4 C1, time is 0 plus C2. Okay, so from here, then we can find C2 is equivalent to 2. Why? Why C2 is equivalent to 2? Because recall back the boundary, when x time is equivalent to 0, it is 2. Okay, so now, what about the upper, boundary? So x when time is 3 minus 12.8, 3 square plus 6.4, okay, plus 6.4 C1, 3 times plus, and C2. Okay, now C2 we already found, which is 2, so substitute it back here in order to get C1. Okay, so now from here, if you do the arithmetic operation, C1 is basically equivalent to 12, isn't it? Okay, so that's how we find it. Okay, so after that, what do we need to do? Okay, so you have C2 and C1. you can substitute it back into function x and also function lambda. Okay, so when you substitute it back, this is how it looks like. Delete this first. Okay, then I can write. So here, remember, C1 equivalents to 12, isn't it? C2 equivalents to 2, isn't it? Okay, so we have here the state variable function. Okay, so the state variable function can be written as this. So xt equivalent to minus 12.8t square, isn't it? Plus, okay, 76.8t. Show me how do you get 76.8t, please. Okay, and then plus 2. Alright, so this one is state variable. Okay, now what about lambda t, the co-state variable? The co-state variable now becomes minus 4t plus 12. Okay, so this is co-state variable. Okay, but this is the function. Okay, so lastly, we can find the final solution because we already have the function for xt and lambda t. Okay, co-state and also state variable. Okay, now, so we can find the final solution for control variable yt. Now, we need to find what is yt. Okay, so here, we know that, okay, earlier, we know that we found this, isn't it? Remember, yt equivalent to 0.8 lambda from the previous, exercise. Okay, so here, see equation 2. Okay. Okay, from 2, we have this. So, what is yt? Okay, so yt, substitute this. Okay, so 0.8, and we know what is lambda, isn't it? We already know what is lambda. Lambda is this one. Okay, so in bracket minus 4t plus 12, isn't it? Then we can have equation for control variable, which is minus 3.2t plus 9.6. So you have 3 equations now, xt, lambda t, and yt. Okay, now what you need to do next is to find y value at starting point 0, time equal to 0, and time equal to 3. Then you can find y at time equal to 0 what? Y at time equal to 3 is what, isn't it? And then from here you can solve all of them. You can find x, okay? You can find lambda, you can find y. So it's very easy actually. Now the calculation is actually easy, but make sure that you understand what you are doing. Okay, so you must understand that x is actually the argument, y is actually the argument also, but lambda is just the shadow price or the Lagrangian multiplier. Okay, so try this exercise. If you can see here, this exercise, I jump a lot of steps. Okay, I don't show you the calculus. So when it comes to exercise, you need to show every single steps, though I don't show it in the exercise here. You must show it. And as you can see here, when I explain to you the step, I didn't write substitute here and to this. I just write few of them, substitute lambda t into x dot equation and whatnot. Okay, but you have to do it. Yeah, you have to do it even if I don't show it to you here, because if I read your equation and your work and I don't understand what you are doing, then I don't give you any marks. Here I keep explaining to you by talking to you in the video, but when you give me the answer in writing, if you don't write it down, then nobody will speak for this paper, for the answer that you have written. So you make sure that you explain thoroughly what you are doing. Okay, so this is Hamiltonian. Try to look at all other exercises also and try all of them, because this Hamiltonian function is a very useful function at the higher level of study of postgraduate, because from there you can understand how certain certain economic variables can change over time. Okay, sometimes it's just a matter of time. So then you can understand why people keep saying that no, you relax, it's just a matter of time. That means certain things can change over time, not because of other determinants, but because of time itself. So this is one example of it, the Hamiltonian function, the optimal control theory. Okay, so that's all for Hamiltonian. Thank you.